Hello students, myself Birjen Bahadur Vishwakarma, working as Assistant Professor in DAB College, Muzaffarnagar. Today I am going to explain about proton nuclear magnetic resonance spectroscopy, that is proton NMR spectroscopy. First of all, we understand what is the spectroscopy. What is the spectroscopy? Spectroscopy is the technique by which we analyze the electromagnetic radiations absorbed, emitted, or scattered by the matters. So, in spectroscopy, we analyze the absorbed, emitted, and scattered electromagnetic radiations. There are different types of electromagnetic radiations. These radiations are arranged in decreasing order of energy. Radio wave is used in NMR spectroscopy. Microwave radiation is used in rotational spectroscopy. Infrared radiation is used in vibrational spectroscopy. Ultraviolet and visible radiation used in electronic spectroscopy. Gamma rays used in X-ray diffraction. X-ray used in X-ray diffraction. Gamma ray is detected in mass bar spectroscopy. So different types of radiations affect on molecules in different ways. These radiations give different types of spectroscopy. Now let us start to understand proton nuclear magnetic resonance spectroscopy. Electrons, protons, neutrons, which spin quantum number is half. They spin about their axis to produce magnetic field. So when they are placed in magnetic field, interact with magnetic field, means electrons, protons and neutrons behave as like tiny bar magnet. When they are placed in magnetic field, they are attracted or repelled by the magnetic field. The atomic nuclei whose nuclear spin quantum number I is greater than 0. They behave like tiny bar magnet and they give NMR spectra. Atomic nuclei such as proton, carbon 13, nitrogen 14, fluorine 19, phosphorus 13, etc. Their spin quantum number I is greater than 0. So they are NMR active nuclei. And the atomic nuclei whose nuclear spin quantum number I is 0. They are NMR inactive, means they do not give NMR spectra. And the atomic nuclei which nuclear spin quantum number I is greater than 0, they give NMR spectra. And when these NMR active nuclei are placed in magnetic field, they go into 2+1 spin orientations. Here I is the nuclear spin quantum number. The I value of proton is half. So in the presence of magnetic field, proton goes into 2 into half plus 1, that is 2 orientation. Means in the presence of magnetic field, protons go into 2 spin orientation or 2 energy levels. The I value for deuterium is 1. So in the presence of magnetic field, deuterium atomic nuclei go into 2 into 1 plus 1, that is 3 energy levels. Means deuterium atomic nuclei goes into 3 energy levels in the presence of magnetic field. Now let us see for which atomic nuclei I value is greater than 0, and for which atomic nuclei I value is 0. The atomic nuclei which atomic number and mass number both are even, their nuclear spin quantum number are 0. Uh, the atomic nuclei whose atomic number is even and mass number is even, their nuclear spin quantum number is 0. If we take an example, carbon 6, 12. Here carbon atomic number is 6 and mass number is 12. In carbon, number of proton is 6, number of neutron is also 6. Here the proton, 6 proton paired up in 3 pairs, and 6 neutron also pair up in 3 pairs. So if the atomic number and mass number both are even, the proton and neutrons pair up, and the magnetic moment of to each other cancel. They cancel out magnetic moment. So their magnetic moment are 0. So and when the atomic nuclei which atomic number is odd and mass number is even, then their nuclear spin quantum number may be 1, 2, 3, etc. And when the atomic nuclei, their atomic number odd or even and mass number are odd, then the I value for their half, 3 by 2, 5 by 2, etc. So in both these conditions, these atomic nuclei, these type of atomic nuclei are NMR active, and if the atomic nuclei which atomic number and atomic mass are even, their nuclear spin quantum number 0, so they are in NMR inactive. Here I value for proton, carbon 13, F19, phosphorus 13 is half. So these are NMR active, and I value for proton to deuterium and nitrogen 14 is half. So they are also NMR active and give NMR spectra. In the absence of magnetic field, protons spin randomly. When the magnetic field is not applied on proton, they spin randomly. There is no certain direction of spin. Someone is spinning this direction, someone is spinning in this direction, and so in the absence of magnetic field, protons spin randomly. But when they are placed in magnetic field, protons go into two energy states, into two orientations. First is the aligned orientation. This is aligned orientation. In this orientation, the direction of applied magnetic field and spin of proton are same. And this aligned orientation, also known as alpha state, and the energy of aligned orientation is low. So this is a low energy state, and some protons go into opposed orientation. Opposed orientation, this orientation in is known as beta state, and the opposed orientations, and in opposed orientation, protons have high energy. So in the presence of magnetic field, protons go into two energy level, low energy state, alpha state, aligned orientation, and opposed and in opposed orientation, beta state, or in high energy level. So protons separate into two energy level. No magnetic field, protons spin randomly. In the presence of magnetic field, they go into aligned state, low energy state, and opposed state. that is high energy state. And also, a type of motion that is called precessional motion. What is the precessional motion? Precessional motion, here precessional motion is the motion, here the proton is spinning and inclined with theta angle and revolve around the axis of external applied magnetic field. This revolution of spinning proton around the axis of external applied magnetic field is called precessional motion. And the precessional velocity here omega is directly proportional to strength of applied magnetic field. Here omega is the precessional velocity. This is directly proportional to beta naught. Beta naught is the strength of external magnetic field. So omega is equal to gamma beta naught. Gamma is the gyromagnetic ratio, and this is equal to 2 pi nu upon h I. So here omega is equal to 2 pi nu, precessional velocity. If we place on this value, omega value, here we will find 2 pi nu is equal to gamma b naught. Here so nu is equal to gamma b naught 2 pi. Here omega, here gamma upon 2 pi, this value is constant. So omega nu directly proportional to b naught, means the precessional frequency is directly proportional to b naught. B naught means strength of applied, strength of external applied magnetic field. What is the precessional frequency? Number of revolutions per second made by the magnetic moment vector of the nucleus around the external magnetic field is called as precessional frequency. Means at 1.4 Tesla, proton shows 60 million times per second precessional frequency. Means the precessional frequency is 60 megahertz, and at 2.4 Tesla, proton show 100 million times rotation per second. That is precessional frequency 100 megahertz, and 14.1 Tesla precessional frequency is 600 megahertz. So the precessional frequency is directly proportional to the strength of applied magnetic field. Now let us understand transition of protons. As we know that when magnetic field is applied on the proton, they go into two energy states, aligned and opposed orientation, low energy and high energy state, and in both orientations they show precessional motion. When we applied correct radio frequency on low energy state, correct radio frequency, here we applied correct radio wave frequency, then this low energy state proton jump into high energy state protons. Means aligned orientation proton goes into opposed orientation proton. Means low energy state proton goes into high energy state proton. So by absorbing radio wave frequency, proton gets excited. So this is the transition of proton, and proton absorbs delta E energy. So this is the transition of proton, and when the excited proton returns to ground state proton, it emits radio frequency. It emits radio frequency, and this frequency is detected in the form of NMR signal. This frequency is directed in the form of NMR signal. So by the transition in the radio wave frequency, here we get NMR signal. Uh, now, now in the molecules, protons are in different electronic proton. Now in the molecules, protons are in different electronic environment. Here, if we take CH4 molecule, here the environment of four protons are same. So all four protons so absorption at a particular magnetic field, at a particular external magnetic field. If we take this example, methyl alcohol, here two set of protons. The electronic environment of both set are different, so they show transition at two magnetic field. Here the OS proton so at a certain so absorption at a certain magnetic field, and CS3 proton so absorption at a certain magnetic field. So the here for the transition of nucleus, the precession frequency and radio wave frequency should be matched, then transition is possible, otherwise not. This condition is called as nuclear magnetic resonance. The precessional frequency and radio wave frequency should be matched for the transition. NMR spectra is recorded by two methods. By variation of magnetic field strength, keeping constant RF value. Here RF value is constant, and here B will vary only magnetic field. And the second method is by variation of frequency of radio wave beam, keeping constant magnetic field. Here magnetic field is constant, and variation of radio wave frequency is applied here. Now we will see how we will calculate the number of signals in compounds. The number of NMR signals in compounds is equal to the number of sets of equivalent protons present in molecules. In this molecule methyl alcohol, this has two set of protons, one set for OH and one set for CH3. Here one proton and here three protons. So in methyl alcohol, two set of protons are present. So it gives two NMR signal. And in methyl chloride, there are two set of protons, so it gives two NMR signal. In ethyl alcohol, it has three set of protons, so it gives three NMR signal. Acetaldehyde, it has two set of protons, so it gives two NMR signal. And in ethyl acetate, it has three set of protons. So it gives three NMR signal. And in cyclopropane, all the protons are equivalent, so it gives only one NMR signal. In methyl cyclopropane, it has four equivalent set of protons. One set is CH3, and this H differ from both this H. This is a separate set, and these two protons differ by these two protons. So there are four sets: A, B, C, and D. So it gives four NMR signal, and here cis 1,2-dimethyl cyclopropane. It has four equivalent set of protons, so it gives four NMR signal. Trans 1,2-dimethyl cyclopropane. It has three equivalent set of protons, so it gives three NMR signal. This compound has three equivalent set of protons, so this gives 3 NMR signal. This CS3 and this CS3 equivalent, this CS2, this CS2 equivalent, this CS2, this CS2 equivalent, because environment of this CS2 is COO, and environment of this CS2 is also COO. So the both electronic environments are same. So it gives 3 NMR signal. In chloroethylene, here it has 3 set of protons, so it gives 3 NMR signal. In paranitrotoluene, it has 3 set of protons, so it gives 3 NMR signal. This set, this CS3 and CSCH, this A set and CSCH are same, because both protons environment are same, and this CSCH set are this CSCH differ by this CSCH set. This CH is different from this CS set, because here the environment is CS3, here the environment NO2. So it has 3 set of protons, so it gives 3 NMR signal. Now we will understand what is the chemical shift. As we know that if a compound has 2 set of protons, they give absorption, they give signal at different magnetic field. So it gives 2 NMR signal at 2 magnetic field. What is the chemical shift? The variation in the absorption position. The variation in the absorption position of a particular set of protons from a absorption position of reference protons due to shielding and deshilding is known as chemical shift. The NMR signal of these 2 set of protons appear at 2 different magnetic field strength with respect to a standard compound, reference compound. So the absorption variation in absorption position of these 2 sets of protons with respect to a reference is called as chemical shift. Here the reference is used as this compound, tetramethylsilane. Tetramethylsilane is used as reference compound. Why tetramethylsilane is used as reference compound? Because it has 12 protons, 3 plus 3 plus 3 plus 3. So it has 12 protons. So it gives a sharp signal at very low concentration. Number of protons, here the number of protons is equivalent set of proton, 12 protons are equivalent. So it gives a sharp signal, sharp NMR signal, and it is chemically inert. It is chemically inert, means this reference compound is not react to another compound, and boiling point is very low. For TMS, boiling point is very low, so it can easily remove from organic compound. Boiling point of tetramethylsilane is very low. TMS, that is TMS, is very low, so it can easily remove from compound. Its protons are highly shielded compared to most of organic compounds. For these protons are highly shielded. Protons are highly shielded. Why? Because here silicon is electropositive. So comparison to silicon, carbon is more electronegative. So carbon attract electron towards itself. So here the electron density is high, and the electrons behave as magnet, and they oppose to applied magnetic field, and the greater the electron density, greater the oppose of applied magnetic field. So their protons are highly shielded. It is soluble in most organic solvent and used as internal standard. TMS is generally soluble in all organic compounds, so it is used as internal standard, internal standard or internal reference. Chemical shift measured in two scale, del scale and tau scale. In del scale, TMS is taken at 0 position, and in tau scale, TMS taken is 10 position. Here, towards TMS, shielding is increased, and towards this side de-shielding is increases. This side, right side, shielding is increases, and left side de-shielding increases. And the same condition is here in del scale. TMS is taken at 0 position, and in tau scale TMS is taken at 10 position. So there are two scales in which we measure chemical shift, and chemical shift is always taken in measured in ppm, part per million. There are some chemical shift value for a specific type of protons. In alkanes, if the hydrogen is attached, the carbon which is attached to groups, alkyl groups, their chemical shift value may be 0.9 to 1.2, and if the proton attached to aromatic ring, their chemical shift value may be 2.2 to 2.5, and if the alpha carbon hydrogen protons, its value may be 2.0 to 2.6. So there are these are the chemical shift value for different types of protons. Here we see the if hydrogen is attached to double bond, its chemical shift value is high, and if hydrogen is attached to aldehydic aldehydic group carbon, then its chemical shift is more high, and in carboxylic group, this acidic hydrogen, this is greater high. So how the chemical shift vary, these depends upon the following, these depend upon the different factors: inductive effect, and isotopic effect, hydrogen bonding, van der Waal effect. There are many factors which affect the chemical shift value. Now let us understand shielding and de-shielding effect. This is the important. Now let us understand shielding and de-shielding effect. What is the shielding and de-shielding effect? As we know that electron spins about its own axis and generate magnetic field. This magnetic field opposes to the applied magnetic field. This magnetic field opposes to the applied external magnetic field. And when the molecules are placed in external magnetic field, electrons also show an other type motion, that is orbital motion type, and produce magnetic field. This may produce magnetic field is called as induced magnetic field. Here the pi electrons circulate in a path in the presence of external magnetic field and generate magnetic field. This magnetic field is called as induced magnetic field, and this magnetic field here in the center, this induced magnetic field opposed to the applied magnetic field, and here right side and left side, and front side and bottom side. Here the in this region the induced magnetic field rain force to the strength of applied magnetic field. So if the proton present in this region is the shielded region, and this region is the deshielded region. Means here the applied induced magnetic field opposes to the applied magnetic field, and this region the induced magnetic field reinforced to the applied magnetic field. So in this region the absorption shift towards high magnetic field, and in this region the absorption shift towards the low magnetic field strength. So in this region protons present, so these protons are shielded protons, and the phenomena is called shielding. And if the protons are present in this region, the protons are called deshielded, and the phenomena is called deshielding. So now let us take example here, benzene. When magnetic field is applied on benzene, this is benzene, planar benzene. Half electron cloud circulate on above the plane, half electron cloud circulate below the plane. So pi electron circulate in a ring current form and generate magnetic field. In the center part here this is diamagnetic region, and the outer part these are the paramagnetic region. So in the benzene protons are present in the paramagnetic region. So in benzene case protons are deshielded, and deshielded protons resonance at low magnetic field, and signal appear at high del value. High del value means the signal appear is TMS here, EMS here, then signal appear at high del value. High del value 0 is here TMS, and high del value. And so in the case of benzene, pi electrons circulate from a ring current and a magnetic field generate, that is called induced magnetic field. And in the center part, induced magnetic field oppose to external magnetic field, while in the outer side this induced magnetic field reinforce to the applied magnetic field. So this is the paramagnetic region, deshielded region, and this is shielded region. Now we take another example, alkene, ethylene. Here in ethylene, this is the carbon-carbon sigma bond. Half pi electron circulate above the sigma bond, and half pi electron circulate below the sigma bond. So the ring current here is formed as. So in this case also proton is present in paramagnetic region. So the signal for alkene protons, for ethylene proton, the resonance of protons occur at low magnetic field. Means the signal appear at low magnetic field, down field signal appear, and the value appear at the signal appear at high del value. So in case of benzene, the signal appear high del value. In case of ethylene, the signal appear high del value. But in the case of acetylene, the pi electron electrons revolve around the carbon-carbon sigma bond. So the magnetic field generate in this way. So in case of acetylene, proton is present in diamagnetic region. So this region is shielded region. So this proton is shielded region. The absorption shifts towards high magnetic field, and the signal appear at low del value. So in case of acetylene, signal appear at low del value, and in case of alkene, in case of benzene, signal appear at high del